droplet.
Thank you very much, Zan. Thank you for having me here, the organizers, and it's really a great pleasure to talk to this audience. As you will see, this is Water Waves meeting, and as you'll see, this is what I call water waves, right? It's basically a terminology for the incompressible hydrodynamics, which you can use a potential theory, but it's actually silicon oil waves. So it's slightly viscous. And I think waves are going to appear here in a quite different way as we've been seeing until now. So this is a problem that was sort of related to a discovery by Yves Couder and collaborators. So here's Yves Couder, which unfortunately passed away in 2019. And he discovered this wave particle association. So basically a new object to be studied. So that's a lot of fun for us that likes modeling. At the time, growing up with Paul and Carlos that's here, and also John Bush modeling this new object, putting waves together with a particle. So something that was not imagined to exist in classical mechanics, this wave particle association, this object that is a composite object. So new math problems arise. And I'm going to try to make as much as I can. Also, you know, it has analogies with dynamics, with things related to in quantum mechanics. It's not quantum mechanics, and it's a problem with it has new dynamics. And I want to really, as much as I can in the time I have, show to you that one thing I find very interesting that we can put in this framework is a nonlinear dynamics of a particle on a potential, just like a mass spring, but on a potential that's dynamic, in the sense of like in the free boundary or kind of framework. It's a particle in a potential of its own making. So in the next instance, what is the potential? And the potential is the underlying wave, or the water wave, actually the silicon wave. And this generates very interesting dynamics. I hope you agree with me as we go along. So the water waves acting as the particle's potential. So from the labs, like some very nice videos that are both from, I'm going to show you, all the videos I'm going to show you are either from Yves Couder's group, which are the black and white, very nice gray videos, and the blue ones are from MIT. So I hope they work. I would test it before. So here are two videos. First, you have this bouncing droplet, this droplet of silicon oil that levitates on a bath of silicon oil. How does it levitate? Because the bath, it's shaking at 80 hertz, so 80 cycles per second, and it does not have time. There's a thin air layer, does not touch the fluid, so it does not coalesce. And if you accelerate a little more, the frequency is, let's say, 80 hertz all through the talk. If you put it more intense, the vibrational forcing, it starts walking. And it's basically, that's the wave particle association, and something that had never, Yves Couder discovered, never seen before in classical mechanics, not imagined to exist in classical mechanics, and that has very complicated dynamics. This is the droplet in real time at Yves Couder's lab, and basically it's a millimetric droplet, but nothing microscopic, so it's something that you can see in classical. So there's a lot of interesting things. So in terms of waves, of water waves, what's the underlying mechanism for this wave droplet system? Faraday waves. So Faraday waves, if you shake a recipient with say fluid water, and there's a threshold above which standing waves appear. Beautiful standing waves as the ones you see there. So these standing waves are basically in the paper, famous paper by Benjamin and Urso, 1954, no droplets, it's just the shaking of this recipient. This pattern arises due to eigenmodes of the Laplacian if the recipient is square or circular or whatever. And in our droplet situation, we're slightly below the threshold. So you would see no waves if there's no droplet. And if it's not shaking, the droplet would just coalesce and disappear. So they live together, this object, this combined object, this association, wave particle association, or wave droplet association. And the dynamics is very, very complicated. Well, I hope nothing comes. I think I have my Wi-Fi on. So as you will see in the modeling, we're going to be, this makes this funny noise. Sorry, it's annoying. So in the modeling, we're going to put ourselves on the frame of the bath. So gravity is going to oscillate. This is the frequency, and this is a very important parameter for bifurcation and all sorts of things that appears in this complicated dynamics. So these are just indicating some of the eigenmodes. And I think that's is what I want to show for this slide. So we're going to be always here, we're always slightly below the Faraday threshold. So the wave exists because of the pressure of the droplet on the free surface. The droplet does not touch the free surface. The droplet deforms a little bit. So in the modeling, I'm going to just have waves, and the presence of the droplet will be felt just by a pressure term that moves around, as you will see in our fluid domain. Okay, so let's keep on going. So if there had this wonderful video with this paper. I mean, this is research-wise, it's like 2005, so it's yesterday in terms of research, right? For the young people may say, "Oh, come on, it's not yesterday." At my age, it's yesterday. So you have here the droplet, the Young's experiment for the droplet going through this submerged barrier. The droplet does not like to walk when it's shallow, so it avoids. And you see this, the pilot wave, as quoted by De Broglie. So you have this wave that guides the droplet. It does not hit the obstacle. The angle at which it comes out is highly unpredictable, which is makes dynamics complicated, but it's good news because, right, quantum mechanics, if you make the analogy, is a probabilistic theory. You have the patterns and so on. So let's see how we study this problem, model this problem. So as I mentioned, this is, I think, something to have in your mind. One way of thinking about this problem, which is, I think, very interesting, is a particle on the potential of its own making. So this has the free boundary, sort of a free interface spirit. You don't know how the potential is going to look just in the next time step, if you think of it numerically. So let me, before I show you the equation, show this 1D experiment. So it's 1D droplets, 2D fluids. So I have one cavity, just like you saw before. This is the wave initially as the droplet did its first bounce. It starts from rest, and this is the time evolution of the wave as we go along. Okay, this is the equation Yves Coudert and group were using before we got into the problem, which is this is Newton's law, mass acceleration, there's sort of a skin friction, some damping on the surface. And look here, this is the wave elevation, and this is how it drives the particle. And you can think of this as the potential. Think of this as a mass spring. Think of this as a harmonic oscillator. So you would have here this eta would be, say, the potential would be kx squared over 2. Right? That's the potential, parabolic potential. And if you shake it like this, okay, like a whiskey glass, which is parabolic, you can try, and you have ice, it would start climbing, right? If you resonant or not. So here you have this wave sloshing here, which will sort of have some secondary type of resonances, all sorts of things that can happen interesting. And I'm going to show it to you what can happen. So this is, you see, the wave takes the particle to the middle of the cavity, and it does this harmonic-like oscillation and guided by the wave. So I'm going to now explore with you, think of this, right? The wave as the potential for this particle doing this harmonic-like oscillator. So this is why, okay, here's my parabolic whiskey glass, which I'm shaking, right? If undergraduate exercise, I mean, not even an exercise, just plug that in there, you get this. The shaking is the periodic forcing. If this guy is near to the natural frequency, you get bigger and bigger amplitudes. So you see that's the way I think when I put many cavities in the next slides, that I designed it, depending on the wave sloshing I can get some sort of near resonant behavior, and the droplet, which will be an oscillator, as you will see, will start having larger range of oscillations. I'm then going to put another particle far away, and one of my goals that I want to show to you is that I can get the two particles far away to be correlated, okay, at a distance. So this is the idea. And look, let's go back to that figure. Here, basically, this looks pretty much sinusoidal, right? So my potential is sinusoidal. If it's shaking just a little bit, okay, I'm going to approximate it for the first term. It's going to be, I mean, that's why I say the derivative of the potential. So if it's sinusoidal and I take the first two terms, it looks like I have a potential for Duffin's equation. If I just leave it sinusoidal, it looks like I had the potential for the pendulum. So this potential of the particle of its own making is also very interesting, because it's like, depending on the regime you are, it's a model that changes uniform or jerseys, if you think of soccer or whatever, from harmonic oscillator to a nonlinear spring to a pendulum, this depending on the wave field that's just beneath it. Okay, so here's the case that I'm just showing. So a sinusoidal, just it's not what we have, but like the sloshing of this sinusoidal sort of underlying wave. Okay, just to set our minds for this underlying potential, which is the wave. Okay, math modeling. So it's going to be a busy slide, but at least I here with experts in water waves, I think with this busy slide, I can convey to you how the modeling is, what are the trickier parts, whatever, but the simple model. So it starts first with Carlos's thesis. Carlos is here interacting with me, Paul, and John, where he did in this paper what I call a 3D fluid, 2D waves. So it's a 3D fluid with no boundaries. Just we wanted to see if we could get a good model for the droplet that had never been done, the droplet with a wave model that would be accurate comparing to the laboratory experiments of John Bush at MIT. Okay, so this is a picture of say Yves Couder. This is a picture of what Carlos's code is doing, and Carlos's model, right? That we use some of the stuff that Paul had already done. Basically, is linear Navier-Stokes, because this is silicon oil, so slightly viscous, some surface tension. Linear Navier-Stokes. You do a weakly viscous potential theory using a paper by Diaz, Diachenko, and Zaharov. You basically get using Helmholtz decomposition. You basically have a div-free and a coil-free part, you know, and so we have a potential, and you get the high order terms of what comes from your stream function, and you basically get a weakly viscous potential theory, something that, you know, actually Paul knew about this paper. I have to give credit to Paul, right? And then said, well, this looks like a model that we really need, and it worked very well. So let me go now to something that's not 3D, 2D. I want to put cavities. I want to trap these droplets so I can have oscillators. So I'm going to go to then 2D, 1D, meaning 2D fluids, 1D waves, and 1D particle dynamics. So here's my setting, because eventually I want to have two droplets set apart to see how two particles far apart can correlate. And let's see what I have here. Yeah, basically, now let me show you the equation. So the notation I don't even have to explain to you, right? We've seen this. And here's the equations. Looks complicated, but look, let me go through it. It's not really that complicated. It's just busy because I have two droplets. Two droplets, two Newton's law, okay? Here, depending on the position of the wave, that the potential, this droplet will feel the slope just like a surfer. If it's higher near the crest of the wave, it moves faster. Near the trough, it moves slower. So we have these two droplets connected to the wave, and the wave model is basically a weakly viscous potential theory, kinematic condition, Bernoulli law. Okay, and then how does this come about? This is just a leading order term that arises from the stream function. So basically, you have shearing, some sort of shearing near the free surface. Here is surface tension. Here is the time-dependent gravity, right? The shaking. And here are two wave makers, pressure terms in the Bernoulli law, which is a manifestation of the droplets as a wave making pressure on the free surface, because it doesn't touch. I don't have to model the droplet. I just have to model the droplet as a wave maker. Wave maker were at the position of the droplet, and this guy will move. I don't know where it's going to make waves in the next, say, time step if I'm doing the numerical method. And then we have then this feedback between these two systems, and that's very complicated, right? So the feedback that this guy goes in here, and also, so here's how the wave affects the droplet, and here's how the droplet affects the wave. And this feedback is highly nonlinear. As I showed you before, if it's a sinusoidal wave, you already see it looks like a pendulum, or it looks like Duffin's equation if you take the first two terms and so on. Oh, and I almost forgot one thing that's very complicated. It's going to come in the next slide, is that this term here is a Dirichlet-Neumann operator, like Walter just mentioned. So with that, I can reduce this 2D domain all the way up to the free surface. And here I use basically something I've been doing for a long time, which is I've been doing waves over topography, non-smooth topography. I can use the Schwarz-Christoffel transformation, Schwarz-Christoffel toolbox, construct this Dirichlet-Neumann operator, and reduce this 2D dynamics only to the free surface. Okay, so let me very quickly, because of this is useful for wave problems. This is how the the Dirichlet-Neumann operator is constructed. So suppose I have two cavities. Here I have actually one. I map it onto a uniform strip. In the uniform strip, it's very easy to do. It's a separation of variables exercise to construct the Dirichlet-Neumann map, where you get the symbol is the hyperbolic tangent, blah, 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 right? For FFTs, with FFTs, it's very easy to compute that. And then I come back, right? But note the following. If I put a single Fourier mode here in the physical domain, because the highly non-uniform stretching of the coordinate system, I get this sort of a very complicated sort of frequency modulation of this Fourier mode. So numerically, in a nutshell, telling you numerically how we dealt with this, is that I do an oversampling for this guy. This mode doesn't need too many nodes, but I put a bunch of nodes so I can sort of well resolve this guy here. It's a spectral method, but if you think of, say, spectral accuracy, it's not 100% spectral accuracy because I use splines to then interpolate and get a uniform mesh here, so I can use the FFT in the canonical domain, and I come back using the Jacobian of the conformal mapping. And what I need for this model, I've done this before for my waves model, what I need is basically the square root of the Jacobian. So M is this metric coefficient, which is the square root of the Jacobian, and it will appear in the equations for the Dirichlet-Neumann map in this way. This is the Dirichlet-Neumann map in the canonical domain, times this guy gives me the Dirichlet-Neumann map in the physical domain, which is the guy I need in my equation. And then I have mathematically reduced the 2D problem to a 1D problem. I also get rid, the good news too is that this guy here is C infinity along the free surface, even though I have corners, it's not smooth on the bottom. But if I'm in epsilon away, I have a smooth coefficient. And that's therefore good news, and let's keep on going, okay? So, okay, so these are two references. We first did this with Paul and John, the cavities, and actually as an advertisement too, is that we also did Dirichlet-Neumann maps in 3D with Davi Andrade that Rafael mentioned, but of course in 3D we cannot use conformal mapping, but it was good to compare and so on. And actually we're just talking with Zan a while ago about this. Okay, so now let me go to numerical simulations and what we've been discovering with this model. With one droplet, we studied with Paul and John when I was at my sabbatical at MIT, we studied tunneling to see how this guy could sort of escape from this cavity and go to the other one, and inspired by that experimental paper by Couder and collaborators, the unpredictable tunneling at a classical wave particle association, their PRL paper. And we found similar things, qualitatively the same and quantitatively pretty good too. Here you see a very long run of the particle trying to tunnel, and we see how unpredictable it is. You don't know when it's going to tunnel, and you don't know how long it's going to reside in a specific cavity. But one thing that's very interesting to note is that when it cannot tunnel, usually there's some action in a nearby cavity. Here there's like standing waves that this guy said, oops, no, I cannot tunnel now. So, you know, start realizing that even though you have this particle, which is something localized, there's something going on in some sort of a non-local aspects of the wave, the underlying wave, and so on. So something to keep in mind. Okay, but I really want to look at two droplets, right? As I said, so my goal, at least at one point and at this talk, is what if I set these two particles apart, and can they be correlated at a distance, right? As we know, for example, in terms of quantum mechanical analogy, right? There's the famous sentence by Einstein, spooky action at a distance, and so on. How can we sort of move in that direction and understanding spooky actions at a distance? Or I think better said, the way we understand it now, and actually already saw some physicists that talk that way, it's not really a spooky action at a distance, it's a correlation at a distance, right? It's not an action. And how is that established, this correlation at a distance? It is established because there's an underlying wave field, and as you will see, I try to show it to you in this not much time I have, that the wave field is able to sort of have some memory. It has already memory. Yves Couder showed memory in some aspect, but it also has memory about the statistics of the droplet. So this is really an important point I want to convey in this presentation. The wave field has some sort of memory of the statistics of this interaction between the two droplets. Okay, so before I tested the droplets far apart, I said, well, let me see if things are right. Let me put two droplets into the same cavity and see what's going to happen. Almost like to check the model and so on. And I was very happily surprised, as I will show you. So this is two droplets. This is not the size of the droplet. It's just the place of the droplet. I on purpose don't put them, of course, symmetric in the channel, in the cavity for them to adjust themselves. You will see them here adjusting themselves, and then they do these cycles. It looks like they're doing something that looks a little bit like a harmonic oscillator, as I mentioned before, and look like they're doing more or less the same thing, but like this, coming in and out at the same time. So I'm going to reflect one with respect to the other to see if they're really synchronized. Okay. And then I'm going to try to see if they're synchronized. I'm going to try to look for cycles in phase space. Okay. So that's in phase space. And I've already put the movie a little bit ahead where you see the droplets adjusted themselves and they're doing some sort of, each one on their limit cycle. One is a blue limit cycle. The other one is a red one. These spikes is the moment where the droplet feels the wave, because then the droplet is bouncing. So it only feels the wave like 25% of the time. All the rest of the time it's flying, right? So it's coupled to, it feels the wave only partial of the time. Those are the spikes. And look what happens. The droplets are there. This takes a long time, so let me go to the computer to save some time. And then at a certain time, this is the water wave, though. The wave is controlling the dynamics, right? At a certain point, look what happens. The two droplets not only fully synchronized, but they go to another limit cycle and stay there. So they stay there forever. Look, in this new limit cycle. So I have no control. We don't have a full understanding of this, of course, like experimental mathematics. They fully synchronize. When I saw this, I said, oh my God, this reminds me something that an Italian professor that was friends with Papa Niccolo, Renato Spiegler, mentioned to me 25 years ago. And some of you weren't even born, maybe, because I said this to myself 3 years ago, so it's already 28 years ago. So Renato Spiegler talked about nonlinear oscillators that spontaneously synchronize. And I found that fascinating, never studied about it. So that's the Kuramoto model. So I said, okay, it looks like we got something that looks like the Kuramoto model. And here's the Kuramoto model. It's a finite dimensional dynamical system, right? Where you have an explicit coupling with the oscillators, and you can have fully synchronized phase locking, partially synchronized, or complete incoherence. So it's a phase transition kind of model that has this critical parameter. If the matrix Kij is just a constant K, you can prove things of a critical K where it's synchronized or this and that. But it's a simplified, this is a celebrated model, very nice, still with some open questions. And this model has also spontaneous synchronization. And there's no explicit term between the two oscillators. What is really, to me, fascinating is that the two oscillators, they talk to each other through an infinite dimensional dynamical system, through the waves. And they only talk to each other part of the time, a quarter of the time. And they synchronize, and you're going to see more. There's a lot of stuff that happens without them talking too much. But it's because I think this underlying wave field has a lot of information and keeps the information there stored. Okay. So I said, okay, great. Now I'm going to set the two droplets far apart. So I put them really far apart. I had to put these two cavities instead of one big one, or else my code is linear, so it cannot go beyond the Faraday threshold. If I make a very big cavity, part of the domain is beyond the Faraday threshold, so it blows up. So I put two cavities, and look, the two waves are here. There's a huge barrier here. It's very faint, kind of the wave field in the middle. And then I asked myself, are these guys talking to each other? Well, actually, before I asked myself that, I was frustrated for some days. I confess, really, for some days, I was frustrated that I lost the synchronization. The Kuramoto synchronization that basically I waited for 28 years or whatever, I lost it. It doesn't look like they're doing the same thing. So I said, okay, let me go to phase space, look at cycles and see what's happening in phase space. Is there like a stable something? So I go to phase space and I realized I removed the spikes. Okay, now it's for a better visualization. I realized there's kind of this stable orbit, if I may call it that way. Since I live I was at an institute where there's a lot of dynamical systems people, I don't like to give names at orbits. So I would say, people say, can you prove this or that? And I can't, right? It's an experiment. It looks like a stable orbit because they stay around. and look what the droplets are doing. They never synchronize. So there you see the spikes. It looks like two crazy guys chasing each other, accelerating, decelerating, making curves, accelerating, decelerating, making curves, always in this sort of racing track here. And then I ask myself, I mean, what can I say about, these two guys? They don't synchronize anymore. So after some days of frustration, and actually in my laptop, I don't have a very good version of MATLAB, whatever. At IMPA, we had one which has statistics too. And I said, okay, I'm going to do then a histogram in phase space and ask myself like a statistical question. Where is the most likely place for me to find these two crazy oscillators, right? Basically, you put a grid on phase space and you do a binning, right? The histogram. If you want, you can normalize it and have like a PDF probability measure in phase space and ask, where's the most likely place I can find these guys that don't seem to be doing the same thing? And then I was very happy because they're identical. So there is some sort of more subtle synchronization, at least in the statistical sense. So I call this then there's a statistical coherence, and something that it's nice for when you think about uncertainty in quantum, this and that, you have something that's statistically indistinguishable, right? The two oscillators, when they phase lock, they're indistinguishable. So now they're statistically indistinguishable. And I said, okay, maybe this is a coincidence, right? So one thing I was asked to, because of the symmetry, whatever, if I do this time by time, this sort of Lego-like picture is not built symmetrically. One builds like this, the other one, and at the end they saturate and look the same. And then I said, okay, now let me remove one of the droplets and let the other one go by itself. The thing is different. So indeed, there is some sort of influence at a distance through the underlying wave field. So, so using the jargon I find in the literature, this dynamics, and since this is like a statistical thing, this system is not separable in the sense that I cannot look at each subsystem individually, right? But then we realized recently, if you use the word separable these days in talking to somebody from quantum, they immediately think about entanglement, which originally the word that has nothing to do with entanglement, just separable in the sense of two subsystems. So maybe a better word, in particular for probabilistic purposes, is the system is non-factorizable, right? In the sense of probability, it's not independent. Factorizable means the probability of A and B will be then probability of A times B. So it's non-factorizable. Okay, so that was interesting and good news. So there's a paper from 2018. So then we started exploring more things. So time average potential versus statistics. So this is something that actually John Bush called my attention. I got to give credit. John Bush called my attention because there's a paper, right? I knew the first paper, but the second one I hadn't paid attention so much. The three authors are here, which is Matt, Paul, and Zan, right? The paper about looking at the average wave field. And so John said, Andre, because now I have cavities and so on, and your paper in particular was for certain regimes. So we said, let's test this for the following. And here's like the theorem they have that they say the following. Let me see if the pointer, let me keep it pointed so there's no noise. This is basically a bouncer at a fixed point, which is a little bit like a stationary Green's function. So I let the droplet pinging at a point until it makes a wave. This is the histogram that you observe. So in the theorem, this would be like a measure, the probability measure. And what the theorem says that the integral of the probability measure against this sort of Green's function, the bouncing Green's function, gives you the average wave field. So I said, well, let's check this numerically. Okay, so here's the picture, right? So I put the bouncer here. I keep it there and there until the wave field sort of saturates. It's quite quick. Then I move it over here and so on. And then this numerically becomes like a matrix vector multiplication. Okay. And then, so here's different regimes for the forcing. If the forcing is not too strong, it spirals in. Here's the harmonic-like oscillator. Here it's starting to get more complicated. And for all these four cases, I tested the formula from their theorem numerically. And here it is. So, here's first, if you look at it in phase space, right? Spiral in, this I removed the spikes. So it looks like a very nice cycle. Here's a cycle that starts to have some period doubling and so on. And now let's compare with their formula. And here it is, right on the money. So the blue one is a simulation. So basically I get the wave field that I saw on that blue graph all the way up. I just average it in time, right? Sum and divide. And the red is their formula, right? The three gentlemen here's formula, right on the money for all these different cases. And look, that sort of the average wave field is quite different. So quite nice to see this formula. And then they said, okay, and this was a process that was a bit unstable, as I'll show you. It's still conditioned, but still was nice. We asked ourselves, actually, I was the first one to say, let's try to invert this integral operator. I mean, let's try now to do something which is very interesting in terms of quantum mechanical analogies, that from the average wave field, can I get the PDF? It's a little bit like going from sort of a Bohmian landscape where you have sort of this wave function and so on, to something more like a Schrodinger landscape, which you have the probability of your particle, whatever. And then if we invert this, right, here's what we get. It's still conditioned, so there are some problems. It's something to be done maybe in the future, but for these four cases, this is what we get. So the blue is the PDF that I compute numerically, right? The histogram, the 1D histogram for, I didn't say it, for particle position, right? And the red one is inverting that formula. So it's a little bit something that that you may call it something like a numerical Born's rule, which is going from some average potential to a particle statistics, and something that also I didn't know, I think was John that said, oh, Andre, what exactly we're doing now, it's something like Born's rule. You have sort of your average, sort of your wave-like potential from wave-like statistics, and we're recovering the PDF. Okay, and this is a moment that I want to make a very special tribute. So it's a bit sad but important moment. I want to make a very special tribute, and it's really sad, which is here are the four authors. This paper is actually under review, and actually, as you saw, maybe I have a new address in for work soon. And actually, I did the interview for at Worcester, and then I went to visit John because it's very close to Boston. And the day I arrived at Boston's John's apartment, coming back from Worcester, John had this very sad news. And I really want to make a very special tribute to a person I worked with for 1 year and I never met because I worked through Zoom, which is Peter Badu. So this is a moment I want to make that Peter, the day I arrived in Boston, he died playing basketball, had a heart attack at MIT at the age of 29. So very sad. And I wanted to use this moment for this tribute to Peter, whom I never met for a matter of hours. So really very sad. Okay, so not cooperation at a distance. So then this paper within people from physics and from with Mathieu, former student of Yves Couder, using the tunneling, we designed this thing, like this scenario where now we're going to have this guy tunneling over here, this guy tunneling over there, and we're going to see the two guys cooperating. Like how? If I had just one droplet, it did that, unpredictable tunneling. If I put now in the 5 cavities only one droplet, first thing to see is that it does the tunneling, and now I have a sort of a metastable situation. It goes to a higher energy guy and comes back very quickly. So then when we put 2 droplets, we saw something which was fascinating, which is if one droplet, it would tunnel this much. When you put the neighbor, it tunnels much more. So you have an enhanced tunneling with cooperating at a distance. Okay. And actually, but that's not, it doesn't happen all the time. It has to do with the size, the width of the mid cavity, which is a guy which is a little bit that does the transmission line for this sort of non-local thing through the wave field. If you make the size of the mid cavity slightly different, it actually can go in the other direction. It doesn't tunnel anymore. The 2 guys inhibit that. And I didn't know this. Of course, the physics guy from the group, Mathieu and the other ones, realized that, whoops, what we have is an analogy of something which is called superradiance and subradiance. which is this. So the observation of spontaneous emissions by, say, ions emission that depends on the separation of the two of them, and that varies with distance in a sort of a sinusoidal-like way with a decay, and we found something similar with the droplets. So other properties from oscillators far away, which can cooperate and so on. And since I don't have much time, let's see, I'm finishing. And droplets that basically isolating droplets. So this is inspired. So I'm going to try to wrap up. This is inspired, and this is actually a very fortunate moment that inspired by the EPR experiment, which is the Einstein-Podolsky-Rosen experiment, where you put two particles together. They might have total spin 0. One is +1, the other is -1. You put them far apart, and then that's where Einstein said the spooky action at a distance. You measure one, say +1, you kind of already know the other one is -1, blah, blah, and how does that happen, and so on. So, and Alan Aspect is actually Nobel Prize winner of last year, right? And then we, in that direction, I'm trying out, let me maybe skip this part, which is trying to put a barrier. I separate the droplets instantaneously after a certain time. Their PDFs change, but they're still identical. And something that I've checked, I mean, I'm gonna now go very fast because I'm finishing, and I checked that, they don't communicate in a sort of supercritical way. There's no way that can happen. And so it really has to do with sort of statistical memory of the wave field. And in this paper that we submitted, we got an example where we were able to violate what would be Bell's inequality, but written in a different way, which is the CH-SH inequality, where Closer is also another Nobel Prize winner, and where you basically play with these droplets as a dichotomic variable. So it's in a low, depending on which cavity it is, one is lower energy because of that metastability, the other one is higher energy. So you can say one is +1, the other is -1, and you check, and this has been violated. It means you get the correlation that's above 2, things that we're sort of still exploring further to get more stringent situations of this. We got one that it's called, actually we're calling it the static Bell test. And now I have to go to a happy moment of praising a young man. Now I have to praise a young man, and this is a happy moment. This young man here that's inspired so much work and great contributions. Happy birthday, Jean-Marc. And here's some references, and thank you for your attention.